Oh, okay. No. Morning, everyone. I'm just setting up. Hi, Syed.
Hello.
Okay. Let me just share my screen. Okay. If anyone has any questions that they want to bring up at the beginning, let's do that now. And so today I'm going to talk about, I'm going to continue talking about volumes and determinants. And I'm going to review a little bit about the Jordan canonical form and maybe talk a little bit more about tensor products. Actually, I think I'll talk about volumes and tensor products today only. Any questions, or I guess you've started the assignment?
So there's a question in the chat about if we have class on Thursday.
Yes, we do have class on Thursday. I think Thursday is the last day of classes. Anything else? Okay.
So Isaac has a question.
Okay, go ahead.
Hi, Professor.
Hi.
I just want to ask if you can talk a little bit about like assignment. Like there's a question says a decomposable tensors, one of the form V cross W for V is in V. I don't quite understand that statement. I don't think that's like quite clear of like what is W and V.
Okay. I'll talk about that today. Don't worry.
Okay, thanks.
Okay. Let's first finish what we were talking about with volumes. So, all right. So remember that a volume, oops, let's say V is a finite dimensional vector space over F of dimension n. Okay. Then we have this idea of a volume. A volume, we're using the term in a funny way. Usually you think of the volume as an as an adjective that, well, you think of it as a property, right? That a certain shape has a volume, right? But I'm thinking of it as a structure, meaning that it's something that the object has to go to the store and buy. Okay, you need to buy yourself a volume. It doesn't come for free. You don't have a volume yet. Okay, vector space has to buy the volume at the store for volumes, and we need to talk about what that set of volumes actually is. So a volume, or if you wanted to, you could call it a volume function, but I prefer not using that term. I prefer just using volume because, you know, like I said, there is no a priori volume, so it's not like the term itself has a meaning unless we define it. So a volume on V is an antisymmetric multilinear what they call N form, or function of N inputs. So this is a volume. It goes from V cross V to the field, and there are N of these. Okay, and I explained what these terms mean last time. I explained that antisymmetric means that in particular, if we have a repetition anywhere in the list, if we have, let's say, U somewhere, and then if that reoccurs, then this will be 0. Okay? It's a kind of funny way of saying antisymmetric. Normally what people would say is they would say, well, okay, if, and I explained this also, is that if you have two vectors, U1 somewhere on the list and U2 elsewhere on the list, then this will be equal to minus V, where we switch. Everything else is the same, but I switch the positions of U2 and U1, and we would get a negative sign like that. And I explained why the first condition is equivalent to the second condition. That's what antisymmetric means. Now, there's also this multilinear. Okay, multilinear means that it's linear in every argument. So antisymmetric means this, and multilinear, right, means that if at any point you get a linear combination, lambda U1 plus U2, right, then this will be lambda applied to the volume where we only have U1, and volume where we only have U2, like that. So in other words, if we keep all of the entries fixed except for one, then it's linear in that entry. Okay, so maybe multilinear and skew symmetric. Sometimes antisymmetric is called skew symmetric. Okay, and yeah. I don't know. I don't think that's useful. Okay. Any questions about this idea of a volume?
So Kai has a good question in the chat.
Yeah, go ahead.
Kai, if you want to go ahead and ask. Okay, so what Kai's question was, this is not necessarily true when f has characteristic 2. So I'm assuming what he's referring to is the antisymmetric condition that you said is equivalent there.
Yeah, that's right. That's right. So the field with characteristic 2 case is a special case. He's talking about the equivalence between these two. So this is equivalent except when the characteristic of the field is 2, which the only field which we've seen like that is F2. So just please ignore this issue. It has to do with the fact that if you look at the proof that I gave that this condition follows from this one, it involved dividing by 2. And the problem is that in Z mod 2Z, 2 is equal to 0. So the field of characteristic 2 is, well, the problem is that there's always a problem whenever you divide by 2, if you're using the wrong type of field. But let's ignore this issue. If you want, you can pretend that I'm over R or over C or over any other field except for F mod 2 or F a power of 2. Okay, so this this idea of a volume. So the first question I want to ask is, what is the set of all volumes on V? Okay, so notice that if V1, or sorry, let me use the curly V, V1 and V2 are volumes, and if lambda is an element of the field, then it makes sense to take a linear combination of them. It makes sense to add volumes together and also to scale them by a scalar. Okay, what do I mean by that? Well, if I wanted to see why this is a volume, then all I would need to do is just evaluate V1, multiply the resulting number by lambda, and then add that number to the number that you get when you apply V2 to those vectors. Okay, and you can check that. Well, it's easy to see just from the formula that if I switch ui and uj, that will switch it here and give me a minus sign, and we'll switch it here and give me a minus sign. So this will be anti-symmetric. We'll satisfy this. And it will be multilinear, just because this is multilinear, this is multilinear, and if I take a sum of linear things, it'll be linear. Okay, so what I'm trying to say, so this means that the, let me call this set vol of V. It's the set of the volumes. Okay, so this means that vol of V is a vector space over F. Okay, so when I say what is vol V, what I'm asking is, what kind of a thing is it? Is it just a set? Is it a vector space? Is it a group? What is it? So what we see is that the set of all volumes, they actually form a vector space. Is that clear? Is that reasonable to everyone, or should I explain further? If you have 2 volumes, you can add them and so on. So for example, if I had one volume which evaluated on the unit cube, let's say that I had a basis, right? And suppose that I had a volume that evaluated on the unit cube to be 1, right? Then I can add it to itself, and I would get a volume that evaluates to 2, right? I could multiply it by a scalar. I could get any, as for the unit cube, I could get any number in the field as its volume. Okay, so just a warning. So usually people exclude the zero volume. Okay, so usually they'll say that if you just take the multilinear function to be zero, yes, it's true that it's antisymmetric because it's just every value is zero, and it's true that it's multilinear for the same reason. So the zero function, which takes any n tuple to zero, that is a volume. Okay, and that zero is the zero of this vector space. So you could say that the volumes are the whole vector space, or you could say that really it's the non-zero elements in the vector space. Define the set of volumes to be this volume of V, remove the zero vector. Okay, so I just want to make a distinction between the zero volume and a non-zero volume, just because that is a vector space, and so there is this trivial element which would tell you that the volume of everything is zero, and that's not very good as an actual practical volume. Okay. Okay, and then the next question is, so this is, let's say, question 1. Question 2, now that I've answered question 1, what is the dimension of vol V? So I can have many different volumes, but what is the dimension? Does anyone have I want someone to guess the answer to this question. So that means that if you know what it is, don't answer. It's only if you're not sure. But you have a thought about it. Can you let me know? What would be the dimension of the space of volumes?
Yeah, Diba?
Is it just one?
Why?
Well, they're all just scalars in the field, and as soon as you have one of them, you can just take a scalar multiple and get any other one of them.
But why I mean, they're not scalars in the field, right? I mean, the result of if you plug in a bunch of vectors, then the result is a scalar, but the volume is a map from from V cross V cross V to F, right? So how do you know that one volume is just going to be a scalar multiple of another?
Is it related to the determinant?
Yeah, it's definitely related to the determinant. I mean, the volume and the determinant are very similar. They're almost the same as we saw last time.
Is it the rank?
Say again?
Rank. Like, is it the rank? I'm not sure.
Rank?
Yeah.
What, the rank of what?
Yeah, never mind.
So, let's imagine that we have a volume. Okay. So what does the volume, you have to think about what information do I need in order to understand the volume in its total, in its full detail, right? So if I gave you a volume, little v, how would you identify it? How would you be able to distinguish it from another volume? Well, what you could do is just take a basis, E1 up to En, and plug it into the volume. That would give you the volume of the unit box, the volume of the unit cube, okay, with the sides being the unit vectors, being the basis vectors, sorry. So you could say that the basis gives a basis box, right? And the volume can evaluate on that basis to give you a number. Okay, so this might be what Diba was referring to, which is that once you know the value of the volume on a basis, that tells you the volume of the basis box, and that's all you really need to know, because if you wanted to know the volume of some other box, you could basically chop it up into pieces, and you could compare it to the basis box, right? And if it was 7 times the size of the basis box, then you would, you know, you would multiply the volume of the basis box by 7. So what I'm trying to say is that in order to know which volume you're dealing with, all you need to do is to evaluate it on a basis. And once you know it on that basis, then any other volume in that vector space is determined by that quantity. So you are right that there is only a one-dimensional degree of freedom, even though this is a function of n variables, right? This seems like a complicated piece of information, right? It's a function of n variables, right? Each of which is an n-dimensional space. So that's a function of n quantities, each of which is an n-dimensional vector. So it seems like it's a function with many, many, many components. But in fact, if you just know a single value of the function, let's say on a basis, that will determine the function. So why, intuitively, so the answer is the dimension is one, since vol v is determined by its value on a basis. Now, why is this? So intuitively, the reason for this is that if I give you a basis, E1, E2, and if the area is A, right? Then I could ask, well, okay, what value does the volume have on V1, let's say W1, W2? Okay, and the idea here is that what you would need to do is make the box spanned by W1 and W2, right? And all you would need to do is figure out the ratio of this to this. So in other words, if you kind of cut this into pieces that are shaped like this, how many times does the blue occur in the red, right? So this is the number of times A fits into the orange box. Okay, but more precisely, okay, we need to use the properties of the volume. Okay, and this is the argument that I gave before, that that, if we take n vectors in V and we wanted to compute, if we want to compute what the value of the volume is on this, then what we would need to do is take each of the given vectors and expand it out in terms of the basis. Okay, and then this will be given by this. So I've replaced now W1 with its expansion in terms of the basis. And each one of them is going to be expanded. sorry that I, let's see, did I avoid this? I'm just writing it in a slightly clumsy way. I mean, it's correct, but notice that because I need a summation index for the first vector, for the second, for the third, and for the nth, I just didn't want to use the same summation index. I could, but it just would be maybe more confusing. So, so anyway, I have a summation for each one of these vectors W because it's an expansion in terms of the basis. And then we can use multilinearity to write this as a sum, to take the sums out. And then I have the volume of EI1 up to EIN. Okay, so this means that now I've expressed the volume of this arbitrary list of n vectors in terms of a sum of numbers multiplied by basic volumes. This is a volume evaluated only on the basis, right? But now what I can use is skew symmetry, right? To say that actually a lot of these terms will be zero because there's going to be plenty of terms where there's a repetition of a basis vector. Like, for example, E1, E1. If the first index is 1 and the second index is 1, then that term in the sum will be VE1, E1. And that's 0. And similarly, we're going to have, so there will be, the non-zero terms are of the form, the first non-zero term is going to look like this: E1, E2, E3, up to En, right? And that occurs when you take the first element of this sum, the second element of the second sum, and so on, right? So the non-zero terms will be like this, but there's also going to be this one, E2, E1. So the non-zero terms are those, let me move this down. The non-zero terms are those for which all basis vectors are different. Okay, like for example, the ones below where I have all different vectors in the entries, right? The only way in which the expressions differ is that they're in a different order. So, but they can occur in all possible orders, right? We could have 1, 2, 3, 2, 1, 3, 3, 1, 2, and so on. Okay, and then I'm going to use the skew symmetry to put them all into a standard form. So that means that let me write the skew symmetry like this. I'll simplify this. I'll say this is a sum of x1 sigma 1 xn sigma n v of the appropriate sigma 1 e sigma n, okay, where sigma is in Sn, the permutations on n and the numbers 1 to n. So you see, what I did was I just simplified this multiple sum by saying that because they have to be different, because the non-zero terms have to be different, that means that it's basically just the list of numbers from 1 to n, except that it can be permuted. So I'm going to sum over all permutations of this expression. Okay, and then I'm going to use skew symmetry again to say that that when you take this VE1 up to EN, right? And if I permute the numbers 1 to n to sigma 1 up to sigma n, right? Then there's a certain number of switches that I need to do. And the point is that whether the number of switches is even or odd, that's called the sign of the permutation. And so I need to put a sign here, -1 to the sign of sigma. So the sign of sigma is 0 if sigma has an even number of permutation of switches. Switching is called transpositions. Okay, and it's equal to 1 if sigma has an odd number. So transposition is where you just take two numbers and switch them and leave everything else alone. Okay, and so this is the point, is that you see that the volume of an arbitrary list of vectors is a fixed quantity. So let me just emphasize this. It's a fixed quantity times the value of the volume on a basis. So so this is basically telling you that that if you yeah, this is just a number. So you see that a volume of an arbitrary list of vectors is this expression multiplied by this number. And this number is just a number in the field. So you see that that there's really only one, it's a one-dimensional problem. If you know the volume of a basis, that tells you the volume. The value in F of the volume on a basis determines the volume. So it's just a single, so the dimension of the space of volumes is 1. So in other words, if you want to define a basis for the space of volumes, all you would need to do is specify what is the volume on a basis. So what you do is you choose a basis for your vector space. You say, I'm going to consider a volume whose value on that basis is 1. Okay, that volume is a basis for the space of volumes. So maybe to be even more specific, maybe to be more pedantic, let beta be, let's say beta E1 up to En be a basis for V, and define V beta in the volumes such that V beta of E1 up to En is equal to 1. Then V beta is a basis. It's a list with one element in it, and it's a basis for vol V. Okay, now yeah, I just want to talk about some properties of this volume now. And let me, okay, so everything that I said so far is basically just a review of what I did last time. Now I want to introduce a new idea now. So if you're bored so far, you can wake up now. So let's say that now let's bring in an operator. So now let's suppose that A is an operator on V, and V is a volume on V. Okay. Okay, so now I can ask the following question. I can figure out, how does this operator on V, which we've been studying for such a long time now, how does this operator affect the volumes of things? So for example, if your linear operator was just a rotation, you might imagine that the volumes would be preserved, something like this. Or if you imagine that the operator is like multiplication by 5, you would expect that the volumes would expand, right? Maybe not by a factor of 5, but maybe some power of 5, depending on the dimension of V. Okay, so the idea is that linear operators, when you apply them to a certain to a certain area, to a certain region, right, it may affect the volume in a certain way, and we want to determine what that is. So there's a question, which is, how does A affect volumes? This is the question I want to answer. It's very simple. Okay, so so this is how I'll do it. So let's say that right. Okay, so if V is a volume, okay, then look at what you can do. You can take this volume, which has a bunch of inputs. Okay, and we know that it's multilinear and skew symmetric in the inputs. Now, what would happen if before you apply the volume, I'm going to sneak in to all the inputs, and I'm going to apply the operator to all the inputs before the volume has a chance to evaluate, right? So I'm going to put the operator in here. This space, this dash, means that it's a space that you can put your inputs. Okay, so now if V was a multilinear function, a function of n arguments, this is now another, let me call this then A affects let me call it pre-multiplying by A. Okay, we get this expression. It's like preparing the inputs before we, if you want, you could think of the volume V as, let's see, which way do I want to do this? Let's say that we have okay. We have n inputs, okay? And imagine that we have a machine that takes the n inputs and outputs something in the field. Okay, and it goes this way. This is what a volume looks like. So actually, let me fix this. Okay, the volume, it takes n inputs and outputs something in the field. And now what I'm going to do is I'm going to take this volume hello. And I'm going to apply A before the volume has a chance. So I'm going to take A. Okay, so you see the idea is that I've taken the volume, which has these n input wires, right? And what I'm doing is I'm putting an adapter in to the wires, but I have to put n of them, right? And now I have something of the same shape. I have n inputs and one output in the field. Okay, and the point is that if I do this, the result is still a volume. This is also a volume. Okay, why is that? Because if you look here, right, what do I need to check to see that this is a volume? I need to make sure that this is still multilinear. So if I look at how it depends on one of the arguments, let's say, well, if I put in here lambda v1 plus lambda, let's say u plus u prime, right, then because A is linear, this will just be lambda au plus au prime, right? And now I have something that is like lambda times something plus something, and the volume is multilinear, so that comes out. So in the end, because this A is linear, and because the volume is linear in this argument, that means that this modified volume is still a volume, is still multilinear. It's linear in all these inputs. Okay, and then the other thing you need to check is, well, what happens if I plug in two of these wires, if I plug in the same vector? Well, if I put in the same vector here and the same vector here, then A of this and A of this will be the same. And so the volume will evaluate 0. So it's still totally skew symmetric or anti-symmetric. So this is also a volume. It satisfies the properties of being volume. Okay, so let me just complete the argument and then I'll answer your questions. So this means that V of A, okay, this quantity is a volume, but we already know that the space of volumes is one-dimensional. So that means that whatever this volume is, it has to be a constant multiplied by the original volume. Since vol V has dimension 1. Okay, there's no other choice. I mean, we can figure out what this constant is, but the important thing that I want to point out is that the way that it must be the case that the way that a linear operator affects a volume is that it multiplies that volume by a constant. Nothing more complicated than that. And this constant, this must depend upon A. Okay, and how do we find this constant? Well, it's kind of easy because you can just plug in any trial value. If you plug in any list of vectors here to the left-hand side and to the right-hand side, then you can just take the quotient of this number by this number and you'll get C of A. So this means that C of A can be computed can be computed by plugging in a basis. So in other words, C of A is just the volume divided by the volume like this. Okay. And this is, what is this? So let's compute the numerator. So this is going to be, so if we write A Ej as the sum Aij Ei, like we normally do, as a matrix, right? So this is the matrix of the linear operator A is right here, this Aij. Okay, then this will be the first column, the second column of A. You know what I mean? Like the columns of A are precisely what A does to the basis vectors. So this will be let's see, it'll be a sum of A I 1 1 yeah, this is fine. AI1 okay, divided by the volume of E1 up to En, right? And then we can compare with our previous descriptions, and this is the determinant of the matrix Aij. Okay, so what is the idea here? So this means that we can conclude that any linear operator it acts on volumes by multiplication by a certain scale factor, right? That when we do this procedure of applying the operator to everything and then applying the volume, right? That the resulting effect on the volume is to multiply it by a scaling factor, by an expansion parameter, an expansion factor, C of A. And that expansion factor is the determinant of A. This scale factor is the determinant of A. Okay, so notice that here the matrix is secondary. In this definition, strictly speaking, we don't need the basis or the matrix of A. This is the cool thing about this definition, is that we have these things which are called volumes. Okay, it's a one-dimensional space. So let me draw a picture. So we have, we have V, and then we have vol V, which is one-dimensional. Okay, and it's just a line. Okay, and the points in this one-dimensional space are the different possible volumes. Okay, then what we have on V is we have an operator that acts on V. And as a result, it has an action on the volumes on V. Okay, but the volumes on V are a lot simpler than V itself. The way that the operator acts on V is kind of complicated. It involves Jordan decomposition and so on. But the way that the operator acts on volumes, it must be very simple because it's a one-dimensional space. The only way a linear operation can act on a one-dimensional space is by rescaling by some number. So that means that there's a natural number associated to every operator, and that number is the determinant. This is just multiplication by a number, which is determinant A. And the cool thing about this definition is that we do not need a basis in order to determine the determinant. The determinant is just what the operator does to volumes. That's all. It's an expansion parameter. So the determinant is a scale factor. It's the scale factor by which A acts on volumes. And if you wanted to compute this scale factor, that's where the basis is important. To compute it, it's good to make this computation where, where we want to plug in a basis, take a basis, apply A to it. When you do that, you're going to get the matrix of A. And then you divide by this kind of unit volume, standardized volume. And then you get this alternating sum of products. You get this crazy polynomial, nth degree polynomial in all of the entries of the matrix. So this is some degree n polynomial in the entries of A. Okay, but the important thing is that maybe we can, so note, we can tell from this definition that the determinant of A does not depend on the basis we use to compute it. So in other words, if we have a matrix Aij, well, let's say that M is a matrix, an n by n matrix, then then if I wanted to take the determinant of P M P inverse, this would be the same as the determinant of M. Right? This, in other words, what I'm saying is that if you take an operator and you write it in one basis as a matrix and take its determinant, that should give you the same number as if you had chosen a different basis to express your operator. That the determinant is a property of the operator and not of its matrix representation. So, and we end up with a kind of a matrix identity like this, which tells you that the determinant is unchanged when you do conjugation by P. Okay, I want to do some more properties of the determinant, but I'll open it up to questions because I've said quite a lot.
Okay, so Jack has a question.
Hi, Professor.
Hi.
I was just wondering, so this whole idea of pre-applying an operator to the vectors of which we're computing the volume seems like intimately related or really, really similar to the idea of the dual map, where, you know, you're kind of like, you have like some kind of, I guess, dual map, and you have, I guess, like a map on a vector, and you're sort of pre-applying that map to the vector, and then you're applying the map from the vector space to the scalar.
Absolutely.
So I was wondering if this could be interpreted as like a more general form, because it seems like almost identical.
Yeah. So so notice here that the volume, okay, what does a volume do? It takes n inputs in V and outputs a field, right? So that means that the volumes are kind of related to the dual space. A dual space is a dual element is more like this. It has one arrow. Oops. Right. So a dual element looks like this. It's a linear map from V to F. Okay, but these volumes, they're kind of like dual elements, but they take n inputs So sometimes what people do is they call this, the usual dual, they call this a one form. It's a function that has one input and then a numerical output. But this, you might call this an n form because it has n inputs and it's linear in all n of the inputs. So there's a generalization of the dual space, which is, you could say, it's the n-fold tensor product of the dual space with itself. Or another way of saying it is that they're like n valent or n-ary dual space. So it takes n inputs in V and one numerical output, and it's linear in every one of those inputs. Okay, so that's like a generalization of the dual space. And then the way that the operator acts on the dual space here by the dual operator is exactly this. It's that we pre-multiply by the element, we pre-multiply by the operator. It's just that now, because there are inputs, we need to use n times that. We need to do it n times. We need to put n copies of it. So this is just a slight generalization of the dual space. So you're right about that.
Gotcha. Thank you. Just like a really quick follow-up to that too. I've seen certain people like define like tensors, like multilinear maps of vectors and one forms from like kind of like a product of like vector spaces and like dual vector spaces to a field. So like, how would you like reconcile that more general definition with like this kind of stuff that's been presented?
Yeah, I'm gonna talk a little more about tensor products later, but maybe you should ask an office hour, because
right.
I mean, I would love to have a second, another month to do tensor products completely, but unfortunately we don't have time to do them completely in this class. But anyway, I'm trying to do as much as possible. Okay, so let me just look at some properties of the determinant first. So, okay, so don't get confused by the fact that, so we can, so the determinant of an operator is defined as above. But it also has an expression, and if A is an n by n matrix, determinant A has the formula star, this formula here. It has this alternating sum of products, which I explained last time. So so you could think of it, there's a kind of more abstract way of thinking about the determinant, that you don't really need a basis, you don't really need a matrix in order for it to be defined. It's just a scale factor by which the volumes are multiplied. Or if you wanted to be more specific, you could choose a basis and actually express the determinant as an alternating sum of these nth degree monomials, which are built from the entries of the matrix of A. Okay, those are the two, if you want, they're the sublime and the profane, or what do they call it? The sublime and the profane. Those are two approaches to the determinant. Okay, now I just want to point out that there's something called the Laplace expansion, which is the method that we normally use to compute determinants. For explicit computations, we use this thing which is called the Laplace expansion. And let me explain it now. So let me just take a special case just to give you the idea of it. Okay, suppose that your matrix is like this. Now, so let's say that E1, E2, and E3 is the standard basis. And let's say that we have a volume which evaluates 1 on the standard basis, so that this determinant, right, is, all I need to do is apply v like this, and then the denominator will be 1. So in other words, the determinant of A is just the volume of, A11 E1 plus, I'm looking at the first column, A21 E2 A31 E3 in the first entry, and in the second entry we put A12 E1 plus A22 E2 plus A32 E3, and then in the last entry A13 E1 plus A23 E2 plus A33 E3. Okay. So Laplace expansion, it goes like this. It's a way, so we want, it's just an algorithm for simplifying this. We want to simplify this. And the way that we do it is we choose a position in the matrix, like we choose a certain row or column. So let's say if I do the simplest one, suppose that I choose a certain row like this. So the first row is going to be these entries. And yeah, so the idea is just that I want to kind of use the multilinearity to take out these terms first. So for example, this will be let's see. So actually, let me first do the first column. It'll be easier to see it that way. Let's choose the first column. Let's say Laplace expansion along the first column. So the first column is right here. And so the idea of Laplace expansion is just use multilinearity in the first argument to simplify. So this will be equal to A11, okay, and then I'm going to have 2 entries, okay, plus A21 plus A31. Okay, so you see what I'm doing? I'm just expanding out the multilinearity in the first argument. That's what Laplace expansion means in the first column. Okay, now the question is, what am I going to put here? I have to put these 2 entries. I have to put here A12 E1 plus A22 E2 plus A32 E3. And then I have to fill in the third entry, right? Okay, but notice that because I did the expansion in this way, this element here, this first element is E1. And that means that I do not need to put the E1 components of the second and third entries, because we know that if there's a repetition, E1, that term will not contribute. That will be 0. So, so in other words, I can forget about the E1 parts. Let me just write them out. E13, E1 plus E23, E2 plus E33, E3. Sorry. Okay, and the E1 components, it's unnecessary to list them there. Okay, and similarly here, I can just put A 1, 2, E1. E1 is okay, and then A 3, 2, E3. And then here I put A 1, 3, E1 plus A 3, 3, E3. You see what I mean? That now what is occurring in these terms, let me write the last one, A12 E1 plus A22 E2, and here it's A13 E1 plus A23 E2. Okay, so I don't need to write the E1 in the second and third. I don't need to write E2 here, and I don't need to write E3 here. Okay, and then if I compute this, if I compute V E1 A22 E2 plus A32 E3 E23 E2 plus, oh sorry, how did I change from A's to E's? That was bizarre. This should be an A. That's strange. And then I did it again. It's like a hardwired thing. And okay. All right. Then we have A23 E2 plus A33 E3. Okay, I'm just repeating this one. Okay, and what do you see? So we really only have 4 numerical entries here, right? And this volume is like multilinear in these two, and in both of these entries. So this thing, this quantity here, it looks like a volume of 1 dimension less. It looks like it's a volume only in these 2 entries with these 2 dimensions, E2 and E3. So this appears like this quantity appears like a volume of a 2-dimensional a volume in 2 dimensions, in 1 dimension less. Okay, and we know how well. Okay, so the this will give A22 A33 minus A32 A23 times the volume of E1 E2 E3, okay, which I already chose to be 1. Okay, so this means that what I get in my as a result of this, so let me write determinant A here, and what I get for determinant A is A11 times A22 A33 minus A32 A23 times the volume of E1 E2 E3. That's the first term. The second term is A21 times, if you look at the expression here, this is it's exactly the same as this, except that the ordering is different. Instead of E1, E2, and E3, it's E2, E1, E3. But it's okay. I'll just treat it exactly the same way. Oops, sorry. What I'll do is I'll write it as A12, A33 minus A32, A13. And now I'll put the volume in the order that it appears in the second term, which is E2, E1, E3. And then the last term is going to be A31 times E1. Oh, there was another one. A12 and A13. So then I'll get A12, A23 minus A22, A13 with a volume in this order, E3, E1, E2. Okay, and if I write this out, it's going to be A11 minus A21 Okay, so let me just write the matrix again. Okay, so you see what's happening is that I decided to expand along the first column, and the first term that I get is A11 multiplied by the determinant of this 2 by 2 submatrix. So I'm going to get A11. The A11 shoots out horizontal and vertical kind of lasers that make you ignore this, and it focuses you on this. So you just get A11 times the determinant of the 2 by 2 submatrix as the first term. Okay, the second term is going to be A21, which shoots out lasers like this, and it focuses you on this 2 by 2 submatrix. Okay, and you compute its determinant, A12 times A33 minus A13 times A32, multiplied by A21. And there's a minus sign because as you go down the row, there's an alternation because you're switching, you're switching which order the volume is coming in. So because of this, because of these volumes here being in a different order, it changes the signs in front of the terms. Okay, and then the last term is coming from A31, shooting out laser beams that make you ignore the column and row that it's in, and it focuses your attention on this matrix, which occurs right there as the determinant. Okay, so in general, this is how the Laplace expansion works, is that you choose a row or a column. So the same technique works for rows, columns, in any dimension. So if I had a matrix, if I had a matrix 1, 2, 3, 4, right, then you could choose any row or column. So for example, if I wanted to choose this row and do a Laplace expansion, then I would get 1 times the determinant of this 3 by 3 submatrix. Okay, minus 2 times this 3 by 3 submatrix. Right? Plus 3 times 3, 1, 6, 1, 2, 5, 4, 3, 1. And then minus 4 times 3, 1, 2, 1, 2, minus 1, 4, 3, 2. Okay. And then you have expanded it in terms of 3 by 3 matrices, and then each of the 3 by 3 matrices you could expand in the same way. You could recursively compute these determinants. So you can see that Laplace expansion is a good way of expanding it out. But really, what Laplace expansion really is, it's just using the basic properties of volumes. It's just expanding using the fact that it's multilinear and skew symmetric, right? And that's how you get the Laplace expansion. And the last thing I want to mention about determinants is that if A and B, so determinants of a product, of a composition of operators. Okay, so it makes a lot of sense that if you have two operators acting on V, and if one of them, let's say A and B, suppose A and B are operators on V. If when you apply A, it expands volumes by a certain factor. And then if you apply B, it will expand volumes by a different factor. Then it makes sense that if you apply the composition of A and B, it will expand by the product of those factors. So what I'm saying is that it's kind of obvious that the determinant of A composed B is the product of the determinant of A and the determinant of B. Okay, so usually this is considered to be an identity involving determinants, but I would say that it's kind of obvious because of the way the determinant is defined. Because if I look at determinant of AB, right, this is the volume where you put AB inside. And then you divide by the volume that you chose. That's what, it's the expansion factor that AB does to the thing. And so then what do you see here? Well, we know that whenever you have, if I just put a bracket here, oh, sorry. Yeah, so, if I put a bracket here, then you see that this is the determinant of B times the volume with A inside only. Because the determinant of B is literally the scale factor that B implements when you plug it in here. Because of the fact that we have B's, I can take it out and I just get this constant scale factor, which is determinant of B. And then I can just use the definition of the determinant again and get determinant of B times the determinant of A, which is just 1. Okay, so yeah, determinant of a composition or a matrix multiplication is the product of determinants. And so that's kind of easy from the point of view of this definition. Okay, right. Okay, and this fact leads to a very interesting a very interesting definition that we can make. So well, okay, let me yeah, so I'm just thinking about whether I want to go down this road. Let me think for a second. Okay, the thing that I wanted to, maybe I'll just give a list of topics that I could cover if we had a lot more time. So number one, the determinant still plays the role of determining whether a linear transformation is invertible or not. So A is invertible if and only if the determinant of A is not equal to 0 in F. So it still plays that role. And you could think that you could think that this is not very difficult to prove because of the whole idea of volume, right? That if you take a basis, then the volume on that basis will give you some non-zero number. So if V is a non-zero volume, and E1 up to En is a basis, then this is non-zero. This is a volume of an n-dimensional box, right? Okay, and then the question is, well, okay, what happens if you apply the operator to this basis? Then you're going to get n other vectors. And the question about linear independence is whether they still form an n-dimensional volume, right? If the n basis vectors are sent so that they are all kind of lined up in a subspace, then the box that they span would be completely flat. And so it would have 0 volume. So this thing is non-zero if and only if if and only if the columns of A are linearly independent. And the columns of A are linearly independent if and only if A is invertible. It's coming from the rank nullity theorem. So, anyway, suffice it to say for today that the determinant is playing, it determines whether a certain linear transformation is invertible or not. And the way that it does that is that it measures how volumes change when you apply the operator. And if this operator kills volume, if it takes an n-dimensional thing and smashes it down to something of smaller dimension, okay, because the range is too small, it's not the whole space, it's not surjective, then the determinant will detect that, and it will tell you that the volume is 0, and so therefore your matrix is not invertible. The second thing is that we can use the determinant to give a formula for the inverse of A when it exists. Okay, and this is a very kind of clever point. So yeah, you can. Yeah, you can say there's a formula for A inverse, and it's given by 1 over the determinant of A times the so-called adjugate matrix of A. Okay, and you can learn about this on your own, hopefully, or maybe in 247 he might do it. And this, if not, you can ask him to do it. This adjugate matrix, the way it works is that for every entry of A, you use the lasers to get down to a matrix of smaller size. You take the determinant of the smaller matrix and you place it in that entry. Okay, so you create a new matrix where the ij entry is the determinant the n by 1 submatrix of A by clearing I row and j column. Okay, so you basically create a new n by n matrix which consists of all possible n minus 1 by n minus 1 determinants of submatrices of A, right? So that involves a lot of work to make this matrix, and then you divide by the determinant of the full matrix, and it turns out that this will give the inverse. Right. Okay, and okay, and maybe something that I should mention, because it relates to what we've done previously, is that if we have an upper triangular matrix, an upper or lower triangular matrix, let's say A1, let's call them lambda 1, lambda 2, lambda n, with anything above and 0 below, okay, that the determinant of this matrix is just the product of the diagonal elements, lambda 1, lambda n. Now, there's many ways of seeing this. Okay, one way is that if you use the permutation definition, what you'll notice is that, for the identity permutation, it tells you to multiply this. It tells you to multiply everything down the first diagonal. Now, whenever you have another permutation, it's going to switch, let's say, 3, like if you look at the numbers from 1 to n, the identity permutation keeps them without changing them, but any other permutation will create a situation where there's a number, where there's a bigger number before a smaller number, right? See here, all the numbers are in increasing order, right? But if I permute this in any way, let's say if I just do 2, 1, 3, 4, 5, right? Then I will have the possibility that I'll have the number a larger number followed by a smaller number, right? And whenever that happens, that means that one of the terms that you're taking the product of will be down here, will be in the lower part. Because we're supposed to, remember, you're supposed to sum over all permutations, right? With the entries being 1 sigma 1. So if sigma 1, like if 1 is less than sigma 1, or if I is less than sigma of I, right, then what happens is that you're going to be, one of the elements in the product will be down here, and that will be 0. So that means that all the higher order terms, all the other plus more terms, plus the permutations, all the permutations vanish because all of the subdiagonal entries are 0. That's one way to see it. Another way to see it is in terms of volumes, right? That if we think of the volume of lambda 1 E1, something times E1 plus lambda E2, something times E1 plus something times E2 plus lambda times E3, right? Then you can see that because E1 is in the first entry, and because of the fact that volumes don't like repetition, this is irrelevant. This is irrelevant. And because E2 is here, this is irrelevant. The only thing that's relevant is the diagonal terms. So that's an even easier way of seeing why the determinant is just the product of the entries. Okay, and then finally, you can use it. So because of this, we can use the determinant to obtain the so-called characteristic polynomial. P characteristic of a matrix is the determinant of some people define it as the other order, but well, this is pretty common to define it this way. So if I write this out, like if A is upper triangular as above, then this is equal to the determinant of lambda times 1 minus lambda 1, lambda minus lambda 2, lambda minus lambda 3, all the way to lambda minus lambda n, and then stuff above here. And zeros beneath. And this will just be the product, lambda minus lambda 1, lambda minus lambda 2, lambda minus lambda n. So what can we say about this? Well, okay, there's a lot of material in the textbook about the characteristic polynomial, but I just wanted to define it in this easy way. So what I should say about the characteristic polynomial is, number one, the characteristic polynomial p car of lambda does not depend on basis, okay? Because if I change A to P inverse, if I do a change of basis, right, then what happens to P car? This is the determinant of lambda minus minus P inverse. But P inverse, I mean, I could write this as determinant lambda. I could write it as like P lambda I P inverse, because the identity commutes with P. So I can introduce P and P inverse like this. And this will be the same as the determinant of P lambda I minus A P inverse. And this, we know that the determinant doesn't depend on the basis. So this is the same thing as the determinant of lambda I minus A. The P's don't have an effect. Okay, so what this means is that not only is the determinant, a basis, let me write this out carefully, is the determinant a basis independent quantity associated to A, but the P characteristic is 2. Okay, so the P characteristic has a lot more information than the determinant. In fact, you can expand the P characteristic as a polynomial in lambda. If you expand this out, what you'll get is lambda to the n. Okay, and then what's the next term? The next term will be lambda to the n minus 1. So minus lambda to the n minus 1 times lambda 1 plus lambda n. And then there's an alternating minus 1. And then the last term is minus 1 to the n times the product minus 1 to the n times lambda 1 product lambda n. So what are these quantities? These are some known quantities. This one here is the determinant of A, because we already computed it up here, right? The determinant is the product of the diagonal elements. Okay, and here they occur as the constant term in the characteristic polynomial. And then this term, you saw it in an assignment. This is the trace of A. So we have a polynomial whose constant term is the determinant, whose n minus first power has a coefficient, which is the trace. And then you have a whole bunch of coefficients which interpolate between the trace and the determinant. All of them are invariants of the matrix. They don't depend on the basis. There's some kind of quantity which reflects properties of the matrix. But anyway, and they have they have nice properties. They're all basis independent. The trace is basis independent, the determinant, and so are all the other coefficients of the characteristic polynomial. Okay, so let's see. Have I given you enough information, or can I overload you even more? Okay, so there's 15 minutes left. Maybe I should stop talking about determinants. Any questions about determinants? I'm going to spend a few minutes now talking about tensors for the first time. Or yeah. Questions on the determinant? I can't stand the fact that the term ends, so that, I would love to kind of continue giving more material, just because we've developed so many good things that now we can talk about a lot of interesting stuff. And unfortunately, like, as soon as you have all the tools in place, the term ends.
So Omar has a question.
No, I don't. I just want to, like, give a proposal if it's possible to have like a mock lecture or something during the holiday.
To have a
just
what?
to cover this, like a
mock lecture.
Like an unofficial lecture during the holiday to cover the stuff that you couldn't get to cover.
Well, but the thing is that the course is not supposed to cover all this. It's just that you're ready now to see a lot of cool stuff, that's just annoying. It's an annoying thing about, I mean, I don't know, I'll think about it, but I have to go on vacation too, Yeah. Any other? Someone else had their hand up. Okay. Anyway, we can talk about it in the office hour. We can talk about determinants to your heart's content. Let me just talk a little bit about tensors. Okay, now, there is no greater disparity between a structure's apparent complexity and its actual simplicity as it is with tensors. Okay, tensors are things that people think are super complicated when they're actually completely trivial. Okay, so what do I mean by that? So it's there is something about tensors which, okay, so the idea of tensors is that from a vector space, V, we will construct new vector spaces, which is called the tensor products. Or actually, let me do the simplest case first. From two vector spaces, V and W, over the same field, we construct a new, larger vector space. V tensor W, which is called the tensor product vector space of V and W. Okay, so it has an intimidating name, tensors. It has an intimidating notation, which is an X with a circle around it, which you never saw before. Okay, and it has a high dimension, which makes it even more intimidating. But the thing that I want to emphasize is that there is almost nothing happening here. Okay, so let me explain what I mean by that. So the tensor product is like someone dreaming. Wouldn't it be great if we could take an element in V and an element in W, and we could take their product, and we would get a new element, right? And then so someone very naive comes to class and says, "You told us about this vector space V and about this vector space W. Is it possible to take a product of two elements, one from V and one from W?" And And then I would ask them, well, okay, is the product going to be in V or is it going to be in W? Right? Do you want the product of two elements? Like if I take an element of V and an element in W, where is the product going to be? Is it going to be in V or W or what? Or maybe they're direct sum, and they would say, well, I don't know. I just want it to be a product somewhere, right? So the idea is that this dream is just implemented in a formal way. So you say, I want to create a product where I can combine a vector in V and a vector in W to make a composite object. And I say, well, okay, just do it. Just take an element in V and put a separator symbol between them, and then put an element in W. So that's it. I've successfully taken the product of V and W. And then you say, you might ask me, well, where is this product? Like, what is it an element of? Is it in the field? No. Is it in V? No. Is it in V cross W, the Cartesian product? No. Right? So where is it? Well, it's in a new vector space, V tensor W. And then you say, well, okay, what is that new vector space? And then I'll say, well, it's these. It's the set of these products, these formal products. So you see what I'm saying? It's that it's almost circular in the sense that it's very unsatisfying because there's almost nothing going on. The only thing I need to tell you is what the rules are between these things. So, this is a formal expression with the tensor product as separator. Okay, you could think of it as an ordered pair, VW, if you wanted. Okay, but the key thing is just what I want. You know, when someone is naively asking that they want a product, right? Then the question is, well, okay, you know, before we even decide where the product should lie, the question is, what do you want the product to satisfy? Do you want the product? Do you want it to be compatible with the pre-existing vector space structure that we have on V and W? And of course, that's what we want. I mean, that's the whole point. So we want the product to be linear in V and W. So in other words, if I take lambda V1 plus V2, this is a vector in V. And if I take the product with W, then whatever this product is and wherever it lives, I don't know, you know, wherever it is in Disneyland, okay, I want it to be true that this is equal to lambda times the V1 tensor W vector plus, and this is the operation of the vector space that I haven't yet defined, right? Plus V2 tensor W. Okay, so what you see is that, you know, the person is making a lot of requirements. They want it to be, and by the way, they also want it to be linear in the second argument. Mu W1 plus W2 should come out. Mu times the vector V tensor W1 plus V tensor W2. Okay. This is the only requirement that the person makes. I could ask them the following. I say, do you want the product to be, do you want it to be commutative? And they say, no, I don't want it to be commutative. I don't want to make any restrictions yet. I just want to be able to take the product of V and W. Okay, if you think about it, it doesn't even make sense for it to be commutative because we're taking the product of V and W, and those are two completely different vector spaces. So we don't, yeah, anyway. Okay, so now I just want you to notice one important thing. The fact that the person wants it to be linear in the first argument and in the second argument means that this equation should hold. And then we have this plus and this lambda. Okay, and this is problematic because all I said was I want elements of this V tensor W to be of this form. But because this plus is here, it's clear that I'm going to have to allow formal sums of expressions that occur in this way, right? So in order for this to be possible, we allow in V tensor W, okay, the following: formal products V tensor W, where V is in V and W is in W. We allow finite formal sums of these. So V1 tensor W1 plus VK tensor WK for any finite K. That's allowed. And we allow scalar multiples, formal scalar multiples. Formal scalar multiples, lambda 1 V1 tensor W1 plus lambda K V1 tensor VK tensor WK. Those are allowed, and which follow the rules, following the rules of bilinearity, of multilinear. So meaning that these rules are assumed to hold. We simply require them by force. Okay, so the tensor product, okay, so I remember when I was told this the first time. When I was told this the first time, I thought to myself, well, okay, they're not really telling me the truth. They're not telling me the real definition of the tensor product. There must be something deeper than this. And I would say that it's not true. There are people who are obsessed with category theory who would say that it's actually defined by a universal property. There's an argument to be made about whether that is true or not. Okay, in the sense that that definition it involves certain steps which are as natural as this definition is. Okay. And you can't avoid this even if you do it the categorical way, because the categorical way at the end you always need to show that the object which satisfies the universal properties actually exists, and so you need to give a construction for it. So what I'm claiming is that I'm telling you the real truth is that the tensor product of V and W is constructed according to a kind of formal list of requirements that I'm going to construct it by hand, that elements of it will be finite linear combinations, formal linear combinations of objects of the type V1 tensor, V tensor W, where this is a formal expression, a separator between V and W. Okay, and we do this following these rules. These are the only rules that. Okay, so you've seen something like this before. I did it in the assignment. Remember how I was talking about? So this is similar to the construction of f of x for x a finite set, where we took finite linear combinations, formal linear combinations of objects in a finite set. Okay, this is very similar, and it's really the same thing. It's really a special case of this construction that I introduced in the assignment. So it is a formal construction of these things. Yeah. Now, what I want to point out is that just notice that if I take an arbitrary element, it will look like this. Can be written as follows: V1 tensor W1 plus VK tensor WK. So there's an obvious question, which is, well, okay, let me do it like this: lambda 1 up to lambda k. So a priori, every element of the tensor product looks like this for some V's and W's and lambdas and for some k. Okay, it's just a formal sum like this. But I can use the rules to simplify this expression. So I can take this lambda and I can view it as multiplying one of these two vectors. So I could write this as lambda 1 V1 tensor W1 plus lambda k vk tensor wk. And so I can really just relabel this as W. Let me just relabel this as W1 tilde. And then relabel this as V1 tensor W1 plus up to VK tensor WK. So it's clear that I can always put any element of the tensor product into a form like this. Okay, now the question then becomes, can I simplify it further? Can I write this as V tensor W for some other V and W, right? Can I always reduce the sums by using a rule like this? You see, like here I have a sum of two elements, but I can absorb the sum into one of the elements, and then it just becomes a tensor product of two vectors. So this has two terms and this has one term. Okay, so such tensors are called decomposable. A decomposable tensor is one that that is of the simplest type. It doesn't have any formal sums in it. It only has the product of two vectors. And the remarkable thing is that not all, and in fact, most tensors are not decomposables, not decomposable. Okay, so when you see, I have to stop now, but let me just give the kind of like incredible importance of this idea of decomposable versus non-decomposable, indecomposable. So in quantum mechanics, okay, a system. So if you have several identical, if we have two systems, two physical systems, they are represented, the states, let's say we have like, in the lab, we have, you know, one cat, and then we have, you know, a cat and a dog. Sorry, I'm limited in, you know. So we have two physical systems, right? In quantum mechanics, there's a vector space associated to this system, and there's a vector space associated to this system. And the states of the cat are given by vectors inside V. So this is the state space. And the states of dog are W. Okay, but now if we stop focusing on each animal separately and we just look at the pair of animals together as one single system, the states of the joint system are vectors in V tensor W. Okay, so the decomposables, what are they? The decomposables are things like this, where the cat is in state V and the dog in state W. When you have a decomposable state, it means that the first system is in one state and the second system is in its own state, and that's it. However, the joint system can be in a superposition of those states. It can be in a linear combination of those states. Non-decomposable is a sum like this. So this could be the cat is dead, and this could be the cat is alive, and this could be that the dog is alive, and this is the state that the dog is dead. Okay? So in quantum mechanics, there can be a state which is like this. It's a formal sum, linear combination of vectors in the tensor product. And the interpretation is weird. The interpretation only makes sense, like normal physics interpretation only holds for decomposable states, because you say, well, the cat is like this, the cat is alive, the dog is alive. But what can be possible is that you have a single state in which either the cat is dead and the dog is alive, or the cat is alive and the dog is dead. But you don't know which one is which. It's a combination of these two states. Okay. And so these states, which are not decomposable, non-decomposable states, are called entangled states. Okay. And the reason they're called entangled states is because it is not the case that one system is in a particular state and the other system is in another particular state. The joint system is in some kind of a joint state, okay, which cannot be interpreted as the combination of two pre-existing states. It is a linear combination of two things like that. And so it doesn't have a classical physical explanation. Okay, so most states in the possible state space are entangled. And it's extremely rare. Well, it's not rare in our experience. In our experience, because we're macroscopic, there's a phenomenon whereby states are pushed towards decomposable states. Like there's a kind of very complicated dynamical mechanism by which most states that we deal with are actually decomposable. But in reality, the set of all states, most of them are entangled. And so the universe is kind of like in this crazy entangled state. And so this is the importance of the tensor product. It's a completely formal kind of construction, but it occurs somehow in the same way, like, you think there's a formal essence in which you take two systems and you consider it to be one system. That's like a formal step where we stop focusing on individual systems and we kind of abstractly think of the full system. That conceptual step is reflected in the formal tensor product of two vector spaces. Okay. Anyway, I hope that helps. Have a good rest of the week and see you on Thursday. I'll stay around for a few minutes for questions. It's not a very attractive cat or dog. I should have taken some JPEGs.
So Diana has a
That's fine.
question.
The animals are really cute. Small technical questions, like since we didn't get to write as many quizzes as was originally planned, are we going to have them dropped?
Since what? Since I didn't hear what you said. Since what?
Sorry, I can't hear you.
I didn't hear what you said. Since we have what?
I heard, it seems she's having a problem. She's saying that, what's it called? Given we didn't get to write as many quizzes as we wanted to,
Yeah.
like we were expecting, are we going to have some dropped or some
There's
extra dropped?
the two worst quizzes are dropped.
I think she means on top of that because of the fact
No.
that
It's
now
it's
the
the same.
quizzes are worth more.
Sorry,
individually.
my sound just disconnected for some reason. Sorry. I meant the quizzes. At the beginning of the semester, you said we're gonna have two quizzes dropped, the marks. But
Yeah, two quizzes are dropped. Two quizzes.
So
are dropped.
it's still a thing, right?
Yeah. I mean, the thing is, I have some freedom in when I'm trying. I will grade and weight the quizzes in a generous way. Okay, that's what I'm planning to do. I'm going to use the grading of the quizzes to try to be generous in the grading, right? I need a little bit of wiggle room somewhere in order to be generous. So that's what I'm going to do.
Okay, thank you.
You're welcome.
All right, so Neil has a question.
Hi, I had one question. So when you defined, obviously, the tensor product and those two linearity rules required, it did seem to imply that that the vector spaces do have to be over the same field Because
Yes, they are over the same field. Yes, absolutely.
so yeah, I guess that is, I guess, one restriction over.
Absolutely, yeah. You need to, you see, like, yeah, you need to be able to take a constant out and put that constant in to the other side.
Mhm.
So that means that this constant has to be very good for multiplying on the V's and on the W's. So they have to, it has to be the same field.
Cool. Mhm.
Okay, so Elliot has a question.
I was just wondering, you're saying how the notion of like a tensor, so it's very relevant in quantum mechanics.
Yeah.
Like historically speaking, was the notion of a tensor, was that structure created for developing the theory of quantum mechanics, or was that already like available and then it was just sort of applied there?
Well, so from a computational point of view, okay, working in bases and with coordinates and all that, these types of tensors were, they were well known in mathematics in the 19th century. So, you know, like Riemann, for example, developed not just tensors in a vector space, but tensors on a manifold, on a curve, like on a surface, and on curved spaces and stuff. So, but they were not conceptualized. Like the conceptual basis of linear algebra, the definition of a vector space, for example, and all that came later. In fact, it came even after quantum mechanics by several decades. So like matrices, they pre-existed quantum mechanics by at least a century and a half. I don't remember exactly, but even Cayley was using matrices. And matrices are essentially tensors, and then you could have tensors with multiple entries, multiply indexed in entries. So yeah, I mean, it's somehow the idea is that the computational formalism of tensors existed long before people really understood what they were as objects. But I think that having quantum mechanics really made a big difference to kind of axiomatizing linear algebra and making it more clear what these things really are. Because, you know, the problem is that when you study it from a computational point of view, what happens is that you discover these expressions like the determinant, and then you discover these quote unquote amazing facts that they are invariant under conjugation, or that they satisfy all these identities, right? So you imagine that you start with something computational, and then you discover all these incredible identities. But really, these incredible identities are only incredible because you don't know what the object is. If you knew properly what the object was, then it would be obvious that these identities hold, right? That's what happened. It's like people understood these formulas, the identities, and then finally the object, which made all the identities clear. That's usually how things happen. It's happened to me in my research many times. I just do the calculations, I figure out how things are working, and then I ask myself the question, what is this object really? You know, if everything is independent of basis, then what is this object? It shouldn't really depend on basis.
Thank you. That's very interesting.
Okay, so Omar has a question.
I do.
I mean,
Well,
your hand is raised.
Oh no. That must have been from before. Sorry.
All right, so Neil has a question.
So I've also heard, I guess, as like the tensor product of V and W could be the set of all like bilinear maps from.
No. From what?
I've heard that there is a way to an isomorphism between this definition of tensor product and the set of all maps that take one object from V and one from W and output a scalar.
No. That would be the dual of V tensor W. So let me just clear up something. So in many reference books and in many textbooks on linear algebra, okay, you know, they don't want to tell you the truth. They don't want to tell you that the tensor product is like I just gave it to you. Okay. Instead, what they do is they say, I'm going to tell you what V tensor W dual is instead. I'm going to say that that these are things like volumes, right? That they take certain inputs and spit out a number. So that's what I did. I explained what a volume is. And the volume is a multilinear function, which takes a certain number of inputs in V. So what that volume is, it turns out, is that it's this is, if I look at a volume, this volume is inside the following. It's, if I take the tensor product of V with itself n times, and if I take the dual of this, what does this mean? The dual space of V tensor V tensor V tensor V. Okay, what does that mean? V tensor V, it means that you're supposed to take decomposable tensors, n of them. Okay, that would be an element inside V tensor V tensor V. And I'm supposed to take linear combinations of these. Okay, now if I have a volume, right, I can of course apply the volume to this decomposable tensor by just saying it's V of V1 up to Vn. And because the volume is multilinear, right, it means that the volume determines a map from V tensor V to the field. We didn't think of it this way. We thought of it only as from the Cartesian product to the field, n times, right? But because V is multilinear, that means that if I take a formal combination of things like this, I can actually kind of enhance or upgrade the volume so that it acts on all of this tensor product. Okay, so the volumes can be viewed as dual maps, dual elements as linear functions on V tensor V. So all I'm trying to point out is that you see, like, I introduced this idea of volume, and you could say that the volumes are actually dual elements to the tensor product of V with itself n times. Okay, so so in that way, you can kind of see that one way of describing dual tensors is by describing multilinear maps.
Right.
Okay, so instead of if I wanted to teach you, let's say, what does it mean to take V tensor V tensor V? Well, then I might, if I was writing a textbook, I would say, well, I don't want to tell them something about formal sums that's going to scare them off. What I'll do instead is I'll tell them what the dual space to that is, because that I can describe in terms of multilinear functions with n, n inputs. So it's a kind of workaround.
I guess I can see maybe for finite tensor products that, I mean, at least there is an isomorphism then between the vector space of the tensor product space and then the space of all bilinear maps, because those are both vector spaces. Well, I mean, there's an isomorphism between any finite vector space and its dual space.
Yeah, so I don't really care if you give me a vector space that's isomorphic to the tensor product. I want to know what the tensor product is.
Right.
I can give you plenty of vector spaces that are isomorphic to a vector space, but it doesn't tell me what the vector space is, right?
Right. Anything with the same dimension, right? It could be oranges.
So what I'm trying to tell you is that the thing you saw in a book is telling you what the dual space is to the thing I'm defining.
And then, so yeah, one
The
last
reason
question.
that they're presenting it that way is a workaround. It's giving you something that's more familiar because they think that studying multilinear functions is easier than dealing with formal tensor products.
And then, so does it have any issues then in the infinite dimensional case where the dual space is no longer isomorphic?
Yes. In that case, you need to use my definition and not theirs.
Okay.
And in any case, their definition is giving the dual space. So they would have to say that the tensor product of V tensor W is the dual of the definition that they give. Anyway, I'm just trying to point out that the idea of tensors is extremely simple, but no one wants to tell you the truth. They always give you these overly complicated definitions, which are not quite right. So what do you want me to do?
Thank you.
All right, so Shijuo has a question.
Yes. So if V equals to W, so could we require the commutative mode in their operation?
Yeah, that's a good idea. So if we look at V tensor V, so in the special case where the two vector spaces are the same, okay, then there's something very special that happens, which is that the group of permutations on two elements. Let me do it in a more, just because the permutation group on two elements is a bit simple. Let's say that we take the tensor product of V with itself 3 times. Okay, then something very special happens, which is that S3, the group of permutations of 1, 2, 3, acts on the tensor product, because if I have, let's say, an element in the permutation group, right, then I can take a decomposable tensor, let's say V tensor V1, tensor V2, tensor V3, and I can apply sigma to this. And what it means is that you're supposed to permute. So V sigma 1, tensor V sigma 2, tensor V sigma 3. So for example, if this is my permutation, then when I act on this tensor, I will get V1 tensor V3 tensor V2. Okay, so what I'm trying to say is that when you take the tensor product of V with itself multiple times, okay, you should think that that now they're all in, they're kind of separate. The separator is in place, which separates n individual vectors in V. And if I have a permutation of the places, then I can kind of reorder them. This would not be possible if these were different vector spaces, right? If this was W, then I would not be able to switch 2 elements because it would not be in the same vector space. So what it means is that permutations act on tensors when they're tensors of V, V, V. And then what you can do is you can ask for, show me the subspace of tensors which are invariant under this permutation. So for example, if I take V1 tensor V2 plus V2 tensor V1, and if this is a permutation, which is just the 1-2 permutation, then when I apply sigma to V1 tensor V2, this will give V2 tensor V1. It'll switch the vectors, and sigma applied to V2 tensor V1 will be V1 tensor V2. So as a result, sigma applied to the sum, V1 tensor V2 plus V2 tensor V1 will be the same thing back again. Okay, so that's the amazing thing that happens when you take tensor products of V with itself, is that you have a symmetric group, a permutation group that's acting on the vectors, and we can look for those vectors which are invariant. They're not affected by these permutations because they're perfectly symmetric, right? And so this these symmetric tensors, so the tensors which are unaffected by permutations are called the symmetric tensors. Okay, and they form a subspace of the tensor product of V with itself. And in the assignment, there's a question where you take the tensor product and you quotient by this subspace. You send all the symmetric things to 0, right? And then you get the skew symmetric tensors. But anyway, what I'm trying to say is that this is you can then see that you can kind of do the following. You can define a different product, which is the following. It's like it's a x tensor y plus y tensor x. And this is called the symmetric tensor product of two vectors. And then this will be commutative. Okay, so this is a trick that you can use to produce, a commutative product. The thing is that when you take a commutative product, the symmetric tensor product, it will be, it will be different from the tensor product, as you can see, because of this equation. So yeah, there's a lot to be said about this. We could teach an entire class about tensor products, symmetric products, and exterior algebras and so on, but such a class doesn't exist yet. But it's a good idea, actually. Someone should create this class, because it's, these whole idea of tensor products, it's really at the heart of quantum computers, of quantum mechanics, of chemistry. Anytime that you have a system that's made of smaller parts, the tensor product is showing up, and so it's everywhere. In applications.
Yeah, it's really interesting.
I agree.
Thank you very much.
Okay, you're welcome. Okay, everyone, see you on Thursday. Thanks a lot, Syed.
Thank you.
Thank you.
You're welcome. Have a good week.